finally, recording. All right, I forgot to start the record. I didn't get too far in, but let me just repeat here what we're going to cover today. So we're going to be going over the extended relational algebra, which is a large part of recitation number 2, which is going to be next Monday. So we have, we've already gone over this a little bit. We have the delta operator, the tau operator, and the gamma operator for grouping. And we're also going to cover this outer join operator, which is like a bow tie with a little bit of an O above it. And then we're going to also deal with recursion in relational algebra. All right, so this all right. Sorry, I just want to make sure I have this placed right. Okay, good. Yeah, now. So duplicate elimination was always pretty simple. What it basically does, it turns a bag into a set. All right. Because remember, the extended relational algebra is under a bag semantics by definition. So when we talk extended relational algebra, we're talking something that's under bags. So sometimes you want to turn a bag into a set, and the delta operator will do that. All right. Sorting is one of those things where the result is actually not a relation, strictly speaking. It's a sorted relation on the sorted attribute. So it's just like a, it's the tau operator basically, just what you do is you just name the list of attributes you're going to sort on. And mathematically, if you want to get like ascending, descending, you just put a negative sign on an integer or on the real or integer or date or whatever it might be. All right. So that'll do that. So this right here, sorting on B here, that means that we're going to have 2, 2, and the ties are broken arbitrarily. So we're going to go 2, 2, and 4. But if we wanted to have it so that we sort, from the top down to the least, we would just put a minus sign there. Okay. Okay. This is still lecture 3, so we're going a little slower than the plan was. But these slides are up there. All right, now we have aggregate operators, which I talked about last time, which basically take in a vector of values, and then what they do is they return a scalar. Okay, so you might have 1, 2, and 5, and if it was max, for instance, then the result would be the scalar 5. So that's what an aggregate operator does. Takes in a vector, right, or a list of values, and returns out well, strictly speaking, it takes in a tuple, but you can envision it this way. So the easy ones are the ones where you're just doing it over the whole relation itself. So sum of A is just going to go through all the A's here. Really, this what this should be. Okay. Sum of A would give us 7, of course, and you can calculate the rest of them. But when we get to the relational algebra, what we have is basically this grouping operator. So what the grouping operator does is it specifies a list of attributes or list, and that list is basically either an individual attribute, which is what's being grouped on, or it's the aggregate function. Okay. So in that slide before, technically speaking, what we would have is something like this: gamma. What was the name of that relation? I didn't have a relation. It would be something like this: gamma sum of A over R. Okay, so let's just say that R basically consists of A and B. All right. So in this case, we're not grouping by anything. We're just doing kind of the raw aggregate calculation. All right, the sum here. So what we'll see here later, though, is kind of a let's go right here to this example here. So right here, what we have here is we say basically we're going to group on A, B. So there's 2 groups here. There's the group 1, 2, and then we have another group. So like distinct ones 4 and 5. And so we group on those. So what the gamma operator does, the first thing it does is it basically will take the grouping attributes and it'll group on the grouper will group on those. And then once you've done that, you basically are forming these little subrelations, if you will. So that would basically be 1, 2, 1, 2, 3, and 1, 2, 5. And then this right here would just basically be 4, 5, 6. So it forms those two groups. What the grouper does, it takes the grouping attributes and it forms a set of basic tables, right? Which are the groups that are defined by these, right? I hope that makes sense to people. And then it will basically do the, then over that, then it will do the aggregate computation. So the average here, so the average between this would basically be 4, the 3 and 5 is 4. And the average between this is, well, that will be a 6, right? So what it will then return then is it basically just computes these and then it prepends the group. So the total thing that we return will be this, right? Will be this. So 1 and 2 and 4 and 4 and 5 and 6. Okay, so this should be all hopefully fairly straightforward. Okay, so we have another one, a special one called counts, which just counts the number that are in group. Okay, so I don't think we need to do too much with this. Eliminating duplicates in aggregation. Okay, so this gets us more into the SQL of it, but we don't really want to deal with SQL quite yet. All right, so this actually does come in the extended relational algebra, but the nulls are ignored in the aggregation. So basically, if you have these null values and you're computing something like a sum or an average or a count, then basically those will just be ignored. So they essentially they don't contribute to the result. So basically, if they're all null, then the aggregation will be equal to null. So if you say average of null and null, it'll give you back the aggregation result of null. If you said average of 1 null and null, then it will give you back the value of 1. Okay, so it's a little quirky there, but null values are always a little bit problematic. Okay, so counts are a little bit different, so it will actually count them. All right. So the number of bars that sell bud, sure. Count, that's the number of bars that sell bud at a known price. I'm sorry, so I mean, this is basically the count, it contributes to 0 to a count. So it's not a null. Basically, what I meant to say here is that if there was nobody who sells, basically, if what happens here is that there's nobody who sells a price for bud beer, if they're all null values, then the whole result of this will equal 0. All right, so grouping. We may follow select from where and group by a list of attributes. Okay, so let me see here. I don't think that's really, I mean, I think that what happens here is the following. This is a very common mistake. Okay, so this right here is a very common mistake. So a lot of times when you first start using these things, you'll get something like this. That is basically, you might think you could find the bar that sells bud the cheapest by this. Bar, give me the minimum price where the selling is of a bud. Okay, so this is not going to be legal. You need to always have, basically what happens is anything that you have up here that's not part of an aggregation here has to be part of a group by. All right, so group by bar, that will give you the, let's see here, group by bar. Is that the way I want to do it? So what is actually, this group by, so let's actually get back to the relation. Let's see that we have this. What we want is we want to get the bar that sells bud the cheapest. And so if we want to do that, let's go back. Let's just do that so we have, basically we have cells. and we have bar and beer. Okay, so that's our relation here. So a bar is selling a beer. And if what we want to do is we want to find the bar that's selling Bud the cheapest, then basically what we want to do is we want to do the following. We want to say basically we want to do a gamma, and then we want to say, well, what is the I mean, I think actually the way we want to do this, let's just actually do this question because this might be helpful. So we want to have the bar that sells Bud the cheapest. Okay, so that's the question we're after. All right. So this actually will be a little. I'm not really sure what we'll need to have to do here. Here, let's just solve it. I would basically do this. I would say, I mean, do people feel like they could solve this already? I mean, you could actually even do this in the classic relational algebra, right? But we don't. We're going to use the extended relational algebra and use one of the gamma. Okay, let me just do this right off the top of the head. I would just basically say this: min price. Sorry, got to have price here too. Okay, bar sells beer at a price. So minimum price. And then I will just go over cells here, and I would just do it this way. I would say beer equals Bud, and put that over cells. Right? So if I do it this way, that will then wind up giving me the absolute minimum price for the beer named Bud. However, that isn't really going to give us the bars that are selling that beer at that price. So for us to get that, we need to do some kind of a theta join here, right? And so this will give us out a single price, right? And so then what we want to do then is we want to basically do a theta join here, where we're going to basically say, so this is giving us out a price, and then what we want, so that's going to give us out a price. But what we can do here is we can say min p. Okay, so if you put an arrow in here inside the gamma operator, that'll do a renaming. No, the aggregate operators are part of the extended relational algebra. If you operate over the entire relation, to select. Okay, one sec. No, they're not. That would be part. That's part of the. This is all extended relational algebra we're dealing with here. So this is okay. Good. All right. So, but I've renamed it here. So I named it to min p here. And so what I'll just do is I'll just do this. I'll say cells. I do a join here, and basically it's going to be a theta join. So I'm going to have it basically say price equals min p. All right. And then over all of that, then I'm going to pluck out the bar name. Okay, so that's. I'm sorry if I to give everybody kind of to see that whole thing. So that's actually how you solve this. The bar that sells Bud the cheapest, right? So it's actually kind of a simple case here where we're not doing any grouping by. Let's just stick with this here so we can kind of like get a good sense of this. What if we want to get like the average price that of beers in each bar? We want to get the average price of beers in each bar. So, and then we want to, and then not only that, we want the average price of beers in each bar and order from cheapest to most expensive. So, and again, I do apologize here because I don't. I mean, I know what it's like to be young. I mean, I've gone. I mean, of course, you can't do this in COVID time and all that. But the thing is, I don't want to like glorify going and finding the cheapest place to drink. All right, I just want to be clear about that because, you know, it's well, but I can see people being interested in that question. I understand that, but but just think of it in terms of like the cheapest juice bar. All right, so we'll just assume that all these examples are over juice rather than beer. All right. Okay, so, but we do want to get this. We want to get the average price of, all right, now I'll just stick with beer. With beer in each bar in order by the cheapest to the most expensive. So that's what we're after now. And we're going to use the sells, beer, and price. Okay, so do people feel like do people want me to do this example? Or, I mean, do you think you can always already do this? Okay, so it looks like people vote for me actually to do the example. All right, so thus I will. All right. So the average price of beer by each bar. Okay, so now if I do this, if I say basically now we're going to take this kind of core thing here and we'll say basically this. We'll say bar. Okay, so this gives us the bar, and this will then, and then we basically want to say average price, and this is over sells. Okay. So remember, sells is beer. Sells is bar, beer, price, and this gamma operator basically it's going to return when you look at the gamma here. I'm just going to just do the renaming here because you can do the renaming. I'll just call it APR price. This when you look at this right here, the number of elements in this list that's under the gamma is going to be how many attributes are in the table that's going to pop out of this. So you understand here the price is going to drop away in this result, the result that comes back from this. All right, so this will give you something like, maybe, I don't know, I can't speak of Umio so much, but it's like, I don't know. Well, there's a real cheap bar in Stockholm. I can't remember what it was called, but anyways, they're all in there. Basically, so you might have this real cheap one where the average price is going to be like 50 crowns per beer, and then another one at the top, and one of these real kind of foo-foo places is going to be like 120 or something. All right. Okay. So we take all that. So that this basically is going to give us back a list of bars, and it's going to give us back a relation that has bar and a price, but it's not ordered yet. So we need to basically take that whole thing and put it into a tau, and then basically do the order and a price. And then if you really want to, you can then project out bar. All right. So I hope that's clear. Okay. So how would you do this in the basic relational algebra? You couldn't. I mean, although some theoretician might say, well, no, you can't really. No, you can't. It just can't do it. I'm trying to think, is there any way you can make, if you bring in some auxiliary relations that have all the arithmetic tables, can you somehow kind of do it? And the answer is no. You can't. It just is unexpressible in the basic relational algebra. Right. Okay, so that showed us the tau and the gamma, and then duplicate. Well, we'll probably get to. Will that work when beer is in the sells table, but there is no group by? Will that work when beer is in the sells table, but there is no group by? I'm not really sure if I understand. I mean, you might get into something like, well, what about null prices coming in here? So is that maybe the question? So, I mean, if you have null prices here, or if you have a beer that never got sold by anybody, or a bar that has no records of anything, how does that happen? I think it had to do more with SQL. Sorry. I mean, I think that in SQL, somebody might, let's see, what would the mistake? Yeah, I mean, in SQL, what happens is that people want to get out the let's see, when does this come up? Because I mean, the thing is that this comes up quite a bit. I just got to think for a second of a good example. Give me the beers. Give me the bars. And no, I mean, I can't come up with a good example, but it'll probably occur to me at one point. But the point is mostly this, is that in SQL, because we're not really doing SQL, we're doing extended relational algebra here. But in SQL, what you'll see is basically somebody doing something like, this is very common, select, and then they list a bunch of stuff from table T, from T. And they'll have something like this. They'll have something like, well, I want the name, and I want the, well, we can do it here. I want the bar. Actually, this will be good. I want the bar, and then I want the beer, and then I want the min price. So for every bar, I want the bars and the beers at those bars that are the minimum price. Okay, so they'll say something like this. They'll do something like this, and this SQL will complain here, because in SQL you can't. Let's see. Let me think of a better example. Bars and average price. This is a better example. I'm sorry. This example will fit exactly in with what's going on here. God, I'm not really sure people can read that. But you say something like this. You say, give me the bars and the average price of beers at those bars from cells. Right? And they look up here and they say, that's exactly what this gamma is doing right here. Exactly what the gamma is doing, right? It's basically saying bar, and it's saying average price, and then, well, I'm saying as here in SQL, as a price. And then SQL says, not letting this go through. And they're saying, well, why not? Look, it's just like this right here. But the thing is that SQL isn't really smart enough to know and to figure out, I mean, you could argue that SQL should be smart enough to kind of say, well, if they're doing this, then they must mean that this should be grouping on bars, right? But maybe it's better just to say, no, listen, we don't want to put too much intelligence into SQL interpreting stuff. So we need to have a group by on bar. Right. So I think that actually is probably, I'm glad that you asked the question, because I think that this will clarify that whole issue of where the misconception happens when people do. Okay, good. Yeah, this is an example where interactive. Thank you very much for that question. So this is an example where interaction lets us kind of makes it a better lecture. All right, the having clause, that has to do with. This has to do with something going on in SQL with. I think I want to put this off when we go back to SQL. But I will come back to these slides later. But what having does is having some special SQL syntax. We'll find later that, I mean, there is no having syntax in extended relational algebra. All right. Well, at least not the standard one we're going to have. But you can always do the same thing as a having. But when we get to SQL, the actual SQL, I'll talk a bit more about havings. Because havings are actually quite they're quite nice to have, actually. No pun intended. It's nice to have a having. And for efficiency, we'll see. Okay, now I want to talk a little bit about this notion of what I was calling recursion. Let's see, what are we looking for in terms of time? Good. So this you can definitely not. Okay, let me just start out here. Let's say, okay, so a lot of times, I mean, just now you're going to hear me poo-poo a little bit here. Some people will say, well, there's graph databases and there's relational databases, and they're one are good for none, and blah 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 blah. And so I just come back and I say, well, I can express a graph in a relation. So how would I, so someone says, well, we want to be able to show something like this, some social network thing, right, where all these people are, certain degrees away from each other, and then, we have this right here. So this is, this is like a social network. right? That's a graph. All right, so they say we need a graph database. They might have a point in terms of efficiency, but let's just say, well, let's just talk about this right here. All right, I just sit there saying, well, let's just do it with in relational tables. I mean, how many tables do we need? Maybe one, called E. Let's do it by two. We say vertex, and that has an attribute A, and then we have edge, and that has A and A prime. Okay, and then I'll give these guys little names here. I'll call him 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and let's just make it a little more complicated. Let's just make it directed. So maybe this is some kind of, we're modeling some kind of flow maybe or something rather than some kind of undirected graph. All right. So what is this going to look like? Well, this table is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. And this table here is going to be, let's start out with the first one. That's going to be 1, 2, right? Because 1 is pointing to 2, and then 2, 4, right? And then 4, 6, and then dot, dot, dot. You get the idea, right? Everybody understands how we can represent this graph here as the in this you know. And then somebody might say, well, do you even need this thing over here? Maybe not. Maybe, who knows? Okay. These are foreign keys. And that's primary key. Right? Okay. Is that clear? Yeah. I mean, I'm assuming this is clear how you could build a graph out of, say we can represent a graph here in a table. Now, if I have an arbitrary table with arbitrary number of attributes, can you represent that as a graph? Well, strictly speaking, yes, through a process called reification, but you're going to lose a lot of information in the process. You're going to lose a lot of capacity in the process, and this thing's going to get very, very complicated. So, anyways, that's a little bit of a, that's maybe something we'll talk about in the advanced course. All right, so that's clear, right? I hope so. Yeah. But now let's say we want to do something like we want to basically say, can we reach 6 from 1? Give me a yes or a no. Someone has to answer that. Can we reach 6 from 1? Yes, good. Can we reach 7 from 1? Then we have another. So there was I'm assuming that was an answer to, can we reach 7 from 1? All right. Now these are really small little graphs, but let's assume this graph winds up being the size of, the whole population of the Earth or something. Okay. All right. So the issue is this: is that can we reach? So in other words, we don't know how many steps it would take. If we're using relational algebra, can I answer the query of give me all of the nodes that are reachable in 2 steps from 1? Can I do that? So all reachable in 2 steps from node 1. You guys understand what I'm asking? All right, can we do it in relational algebra? Okay, do people want to see me do it in relational algebra, or can they already see how to do it? Okay, I guess I should say, I'm assuming people want me to show it. Okay, so let's do it then. All right, so remember this, all right? So this edge cross edge prime, it's a theta join. So I'm going to basically say, sorry, I need to go back here. I'm going to call this to, and I'm going to call this from. So here, let me give the signatures of these things. So edge, the edge relation is the attribute to and the attribute from. Okay. I do a theta join here where basically this E here, which is from, equals this edge is 2. So 2 prime. All right, so what does that give me? Let's make a real simple graph here. There's 1, there's 2, there's 3, and there's 4, just to kind of make it okay. So this is represented as the relation E from 2, 1, 2, 2, 3. All right. So we're going to join these together. So I'm going to make a copy of it, E prime here. And so that's also going to be 1, 2, 2, 3, E prime from prime to prime. Okay, right. And now we're going to do a theta join here where this one equals that one. So 2 equal, there we are. 2 equals 2. So basically what that's going to give us is that's going to give us that right there, these together right here are going to give us, what's the result going to be when we do this right here? It's going to be, all right, this one had better, yeah, he matches here. This guy, this 2, uh-oh. I think I got it all screwed up here. Sorry, this is what happens when you, so 2.
Could you move the paper up a little bit because we don't see.
Okay, sorry about that. Thank you. So I'm sorry, I screwed up here. So this is what I meant. The 2 in the original here has better equal the from prime there. So sorry, 2, it doesn't equal there, but it does equal there. So therefore, the answer is going to wind up being 1, 2, 2, 3. 1, 2, 2, 3. Okay. Then we go to this one, and there's no 3 here. So that's the result right there. Right? So now, if I take this right here, and then I project out the let's see, I gotta get this right here. From, and then 2 prime. Right? So this is from, and this is 2 prime. This is also from prime, and this is 2 rather, sorry. Then I'm going to, if I do that projection there, then actually what I'm going to get is I'm going to get 1, 3. Okay? So that's giving us this right here. What this guy just gave us here is to give us all the things that are reachable from one node to another node via an intermediary. Clear? Okay. So now somebody might say, well, that's all fine and good, but actually, this is I'm just going to take this as an opportunity here to kind of show you guys what an outer join is. Somebody might say, yeah, that's kind of seems like it, I don't know. We want all the hops that are 1 or fewer, right? So we want to retain the underlying graph here. Then what you would actually do, and we'll talk about this later here, but I just want to show this. If we do make this an outer join, okay? If we make that an outer join, then, so this is just kind of, because I see an easy way to show the outer join here. What this is going to wind up doing is it's going to wind up doing null padding here for the ones that don't match. So 1, 2 match, that's fine. But 2, 3, null, null. Actually, this is not a great example, but I'll continue going with it. And then 1, 2, 2, 3. Okay, so then, and we'll also have 2, 3, null, null. All right, so this example is not going to be so useful, but now that I started, I'll finish it. Just what an outer join does is that if the things don't match, so as it's going through here and it's doing the matching across, if nothing matches, it'll just do null padding. It'll just pad out nulls, but at least will retain the original stuff. All right, that's just kind of just the definition of what an outer join is. We'll cover it more. We'll give it more motivation here. Right here, it's actually not that motivated. It's not going to really give us what we want. But I just wanted to kind of bring it up because I brought it up. So that's just kind of a little bit extra syntax to talk about outer joins in the extended relational algebra. But forget about the outer join thing. I just wanted to show it quickly what it means. But let's just continue on with this right here. All right, so that right there shows us how we can get all the things that are going through one intermediary. All right. Now, what if we want to do everything that's like 2 hops? All right, so now let me add another one in here, 5. So all the things that would boink, 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 so that reachability. So basically what you would do for that is you would basically say, I'm going to do an E, and not that one, but E prime, E double prime, okay? And then there's some kind of probably a project. And then I've got to specify all the theta conditions here. But I hope that people see that. If people see that, how I can get 2 hops, right? Okay. And then if you see that, then you can see how I can get 3 hops. But that's not what we're really asking for, because maybe in this original guy here, God, the paper is really kind of, this is becoming kind of ridiculous here with how much paper, but I'm not good with paper also. How much more of it? All right, anyways. Let's just do it this way. All right, so yeah, so we're gonna have some graph here that has a total of 291 hops. And then, so 1 in 299 hops can reach node 45776163. All right, so this one in 299 hops can reach that one. But we don't know. I mean, it could be 292 hops, right? It could be an arbitrarily large integer of hops. So how do we do this in relational algebra without having to write an infinitely large expression? The answer is we can't, if we're just going to stick with relational algebra without extending it with something. And what we're going to extend it with is what's called recursion. All right. So we have this E, which is from E, which is from and to. Okay. So I'm going to do the following. I'm going to say this. I'm going to say that R, we'll do it. Okay. R equals E. Okay. So now R has just been, the E has just been copied into R. Then I'm going to say R equals itself. Okay. So, all right. Joined with E, and the theta join here is going to be R dot, I'll just kind of use the notation here. R dot 2 equals E dot from. Okay, R dot 2 is equal to E dot from, and I'm going to project out of that. Sorry, R dot from and E dot 2. I'll rewrite this to make this cleaner. Okay, so let me just rewrite this again. Okay, so R just gets a copy of E. All right, E goes into R. Remember, E is from 2. And since it's getting copied in here, then R is also from 2. So the signature of R is also, God, Jesus, Michael. I am really sloppy doppy. I don't know what it is. Anyways, these are the signatures. They both have attributes. This one's called from and to. This one's called from to. Right now, they're equal to each other. They're the same exact thing, right? But now watch this. I say R equals, and then I'm going to basically say R theta joined with E, where R dot 2 equals E dot from, okay? Project out R dot from equal and R dot from and E dot 2. Okay. So notice that R is being defined in terms of R. That's a recursive definition, right? So we're involving recursion in the definition of R. This is the base case. So R starts out with just the basic underlying graph. Then what happens is we take R and we join it with the underlying graph again to see what are all the one hops that we can obtain from R using E, right? And then we're going to pluck out, well, what those are. What are all things that can be found in one hop? And then we're going to add that into R, right? So R just got a little bit beefier. It just got a little bit more of a completion. So this is called the recursive transitive closure is the technical name for this. So it's the so now what will happen, of course, is that now R is a little bit bigger, and then we can just repeat the calculation. And this repeats and repeats and repeats until on one particular calculation step, we have R. Let's say that every time we do this, we're going to calculate a new R. We'll call it delta R. So, okay, so R just winds up being E here. We do this calculation, and then we calculate the new R. We'll call that delta R. Right, so basically all the things now that are the underlying graph and also one hop reachable, right? And then two hop reachable, et cetera, et cetera. Once we keep on doing that and we reach a step where the delta R is equal to the R, that is nothing new was obtained in this operation, then we've reached what's called fixed point and we're done doing the calculation of the recursion. But this will end, this could go on for an arbitrary number of steps, but it will end with the reachability relation. So this will actually give us reachability in the graph. Right? Is that clear to people? I mean, maybe. So when we add recursion to the relational algebra, all we're doing, you have to do this now as a program. You can't do this as a single expression. You have to do it as a program, and you just have to kind of start up the base case and then do the recursive definition. Okay. Yeah, it's the recursion. Yeah, the recursion is just defined because I'm saying R equals, and then I'm doing some expression where I'm using R in it, right? So that kind of defines the recursion. And the thing is, we have the base case, we have the induction step, and the question is what ends it? What ends it is when we reach this fixed point where nothing gets added to R. There's nothing new going into R. So that's the definition of recursion. And SQL has a recursive operation in it. And you may say that, wow, do you ever really use this stuff? And the answer is yes, you do. If you're doing things the right way, you use recursion quite a bit. So I mean, yeah, I've used recursion a lot in practical cases. You'll get a lot of cases where what you'll do is you'll have like a class hierarchy. I mean, so how do I say this? Let's say that we say something like that we have a whole class hierarchy of different things that we classify stuff into, and we want to do the deduction that, let's say that we say something like a turnip is a vegetable, and a vegetable is a food product, and a food product is a consumable, and a consumable is a blah, blah, blah. If we say that some particular object is a turnip, we want to have the recursion kind of kick in and have it so it's also all those other things going up the hierarchy. That's done, you do that with recursion in SQL. So that you don't have to, it just makes things a lot cleaner in terms of you don't know the arbitrary depth of the is a hierarchy. So this comes up a lot. So you also have it in bill of sales problems. I mean, this comes up. It's very useful to have. So SQL has this recursion operator in it. So that's kind of like, okay. So it has that. We'll show the SQL syntax for that later. The relational algebra doesn't, strictly speaking, have it until we allow for these kind of definitions. All right, good. All right, so I think we're finishing up on the extended relational algebra here. Might have a little bit more to say about the outer join stuff, but we're going to probably go into SQL in the next hour. So why don't we take our break now and get back at 20 after? Okay, so come back at 11:20. All right, thanks. You can ask any questions in the chat, and then I'll try to answer them when we resume again. Okay, I'll pause the recording here. Okay, I started recording again, which I'm glad I didn't forget about. One second, I just have wait, I have something in the chat here that I need to look at. I don't understand. I got a direct message, but I don't seem to have gotten it. But anyways, I can't see it at least. Anyways, maybe that'll clear up. Anyways, if there's any people have any questions, put them in the chat. I guess the direct message. I'm not sure if direct message is working, but maybe we'll see. You can also send an email. That's also a possibility. All right, so let's go on. Let's finish up the extended relational algebra. And when we do that, what makes line? No, actually, that was an earlier question. So as we do this, then what we're going to look at is we're going to look at the outer join. That's the last thing we're going to look at inside the extended relational algebra. So basically, let's say we have this table here. We have this table R, and we have the table S. And what we want to do is we want to join R with S. But when they don't meet, when we can't find something, we want to join on B. When we can't find something that meets, so in other words, we have 4 or 5 here, but there's no 5 over here, we'd still like to actually have 4 and 5 here, and then just pad it with a null. All right, pad the result with a null. This comes up quite a bit. So for instance, you might say something like, well, you want to get the customers, and then if they have, you want to give a list of all the customers, and if they own a stock of a certain symbol or something, then we want to say how much they own of that, how many shares they own of that stock. But if they don't own that stock, we'll just report 0 or null, right? We want to have it so that we still get a list of all of our customers. And so we're preparing a table where we're getting a list of all of our customers, which is good. And then if they happen to also own some particular stock, we'd like to put that on as a column of the list. Otherwise, we'd like to have that column equal null, right? I mean, that's something that you can see that being asked as a practical question, right? So that's a classic case where we want to use an outer join. All right, so the outer join again, so we have like the customer here. Here's one customer who does own the share. Here's another customer who doesn't own the share, who owns none of the share. So we'd still like to have that customer and their name or whatever it might be, or customer and something they might own or something. I don't know. It doesn't matter. We would like to have that reported and have the null here. And then likewise, it works symmetrically. So if there's something here that doesn't join on, we'd like to have the null padded there. So is that kind of clear what's going on with that? So the way you express that, it's like a theta join. Well, it's like a natural theta join in this case. So it's like, so basically here's a syntax. Here's how the syntax would work here. We have like, there's our normal natural join. If you want to put a theta here, you can do that, and then it turns into a theta join. And then if you say basically like this, if you put an O here, it turns it into an outer join, okay? And that could be an outer theta join or an outer natural join. In this case, actually, it's an outer natural join. All right? So it's going to take care, it's going to do the bookkeeping because it's just a natural join. It's going to do the bookkeeping around the B being repeated and then not repeat the B in the result, okay? And notice that things that don't match, that don't go through the outer join, wind up getting null padded. Is that clear? Kind of what's going on with that, with the O operator? When an O appears above a join, be it a natural join or a theta join, the notion is that it's going to be outer joined, and things that don't match get null padded. All right, I hope that's clear. So a question might be this. It's like, all right, well, we've added this new operation into relational algebra, but I told you that, so then the question might be like, well, is that something that extends the basic expressivity of the relational algebra? In other words, can you simulate, if I give you this, our natural join with or let's just do a theta join here, theta with S, can I make that equivalent to something that doesn't use the outer join? Do people have any feeling about that? This again, we'll kind of make it so that we have a fully clear understanding of what's going on here. One second, let me just get this. Oh, yeah. Sorry about that. Actually, somebody told me about that, and I told them that I would be more careful. I'm sorry about that. So yeah, so here, the question is this, is that maybe I'll just be careful on the next one here. I have two relations. I have R, and we're going to do this abstractly. All right, I have R, and I have S. And then I do a, let's just keep it, yeah, we can keep it as a natural join. So I'll say A, B, and B, C. Okay, those are the attributes. Two attributes here, two attributes here. I'm doing a natural outer join between R and S. Can I write that as an expression that doesn't use the outer join syntax? Do people want to see me try? Or is it, okay. So here's how we do it. We say, so what is this going to be? Well, what it's going to be is it's going to be basically, we want the first we want the ones that where it joins. So basically it'll be R natural join S. Okay, so that will give us the ones that are matching, right? So that's not quite there yet. So we want to union that with something. We want to union that with basically we want the R's where there is no matching S. Okay, where there doesn't exist a matching S. So we're gonna do the left part of this first. So how do we calculate that? The R's, so that these are like basically the R's for which there does not exist a B that they're matching on. How do we actually calculate that? The R's for which there's no B that's on which they're matching. Well, it's going to be kind of a complicated expression. Let's just try to get it worked out here. Basically, we would say something like this. We would say that, okay, well, we want to get the first of all, let's get the B's that don't have a. Let's get the R's here where there does not exist a matching B. So basically, that would be the all right. How are we going to do that then? So the way we're going to do that is we're going to basically say, well, let's just do it as kind of a side thing here. If I say project B from R, okay, that gives me the B's from R, and then I say minus project B from S. Okay, that right there, that just gave me all the they gave me all of the B's in R here where there's not one in S. Is that clear? Can't you just do a theta join and say, no, that unfortunately won't work. Because what that would basically say then, so where it, let's see, how do I say that? I'll get to that. That's a very good point. I want to get to that, the point that was made in the chat here, so I can show that is not going to be good enough to do it that way. We can't just say that they don't equal, because that's true for a lot of them. That's true for a lot of the tuples. If I have, let's say I have 1, 1 here, and I have 2, 3 here, but then I also have 1, 7 here. Well, we can find one here where it doesn't equal, right? This B does not equal that B, but it does equal that one. So this A here, this tuple right here, actually it's not part of the this one does actually have a match in S. Is that clear? We've isolated here. However, if I do this, if I say select the B's and then select the B's here, and let's put another one here. Let's say 7, 2, no, 7, 3. This will give us 1, 3 in this set, and I'll minus out 2, 1 here. So that'll leave us over with 3 here. All right. Okay, so that's right there. Just this will give us those, and then let's basically say, well, here's what we'll do. We'll just say that, and then we'll natural join that with R. Okay, we'll natural join that with R, and then what that will give us is something. This has only 2 attributes. This has A and B. Okay, and so then the issue is that, well, what are we going to do now? So how are we going to be? So this actually work out here. Let's just see here. Then what we'll do is we're going to actually do a Cartesian product. And then I'm going to do a little bit of a cheat here, which I think people are going to say, huh? Can you do that? And I'll basically just put in a literal table here. Null. And I'll basically name this thing C. Okay, so this right here is something new in the syntax, where I'm just putting in a literal relation. So, there's no reason why you can't do that. For just to put in, I could go over here and I could set this thing equal to C and null. Right? This could be, I could basically have over here, I have this thing called Z equals the relation C null. That you can't see, can you? Sorry. Z equals C null, right? Okay, and then I could basically just do a Cartesian product here with Z. Sorry. Okay. Z equals basically just this literal relation which has an attribute C and has a value of null. People see that? So let's look at this thing right here. This gives us all the B's that are in this table here, but not represented here. Right. So this will give us back a relation of one attribute B. And in this case here, it'll be a relation with just one tuple, which is 3, because this is the only one. I plucked out 1, 3 here, and I minused 1, 2, 1 here, and that gives me back 3. Right? Am I right or am I right here? Okay. Good. All right. So this right here then equals 3 basically. I'm going to do has B equals 3 here, and I do a natural join with R. So that'll give us, 7, 3. So this whole thing right here will just be 7, 3. That's the whole result of this guy right here. And now I'm going to do a Cartesian product with null. Okay? So that's kind of what it's showing here. So that's one side of it. That's this one side. So if I union those together, I can union that on top of this. All right. So this right here, this expression here, and I can do the same thing by symmetry over S. So I hope that everybody sees that I can indeed express this operator, this outer join operator, in more basic operations in the relational algebra. Do people all see that or agree? So it's not adding anything to the expressivity of the language. Now, why would we use it anyways, though? So, what's the point of it? If it's not adding anything to the expressivity of the language, why do we use it? Well, there's a very, very good reason why you would use it, and that is, remember, these extended relational algebra, this right here is kind of a complicated calculation. If this winds up being 1 million tuples, and this winds up being 20 million tuples, then if you're doing this kind of stuff in there, you're going to really be wasting time. So if you have this right here, this is going to be an instruction to the actual database system to actually do it the smart way, and then just kind of pad the nulls as it's building the join. So it certainly is important internally to databases to have an outer join explicitly represented in the extended relational algebra. I hope that makes sense as motivation. All right. I think with that, we're done with the extended relational algebra. And there's somebody who brought it up. I remember seeing, and I was kind of impressed. Somebody was doing semi-joins. Somebody was doing semi-joins in recitation, which I think was cool. But we're not going to cover semi-joins. Just to, there's a lot of other little things that you can bring into the extended relational algebra. Let me see, is there anything else that's missing? Well, there's the outer join is the whole left and right variations of it, but we're not going to cover that in the extended relational algebra. We'll cover it maybe in SQL, but we're not going to cover it in the extended relational algebra. All right. And there's a lot that goes on in this extended relational algebra, because remember, just to kind of, again, bring this back to some kind of motivation, the way that things work is that you have SQL, and that gets mapped into an expression in extended relational algebra. Okay, and that actually winds up becoming a tree of all these operators working on operands, and the operands at the bottom are things like tables. Okay, so the actual engine gets this, and then it turns that into an execution plan. So it takes this, and it actually will take that to actually turn this into something that it executes over the database to obtain the answers. Okay. So this extended relational algebra has this relationship with SQL. That's because remember that, just to kind of complete the picture, this kind of classical rel algebra, tup calc went to the classical set-based relational algebra. Okay, but that was just kind of a setup, kind of conceptual setup. this is real world. This is real world. This is the conceptual setup, all right, which has a lot of nice mathematical things you can play around with. But this right here is actually how it goes. So this is grubby. SQL is a grubby language, and therefore this also becomes kind of grubby. So there's a lot of extra little, things kind of hanging off the side that do special things to kind of just for practicality's sake. All right, good. All right, so with that, what we're going to do now is we are officially closing now the whole kind of extended relational algebra, tuple calculus, extended relational algebra. We're going to close that in this course for now, and we're just going to go over to this guy right here, to SQL, because I don't want to cross it out. we're going to focus now on SQL. All right, so SQL will be the language now that we're dealing with, and this is a language that gets this is a real language. It gets used, so that's nice. All right, so let's just have this as kind of one of the running examples as we do some of these SQL queries. So we have a stock symbol, and then we have a stock with it says a symbol, and it has a price at a particular time, and it has a type, retail. We might have another one here like what was it, AMC, which maybe at a certain time, certain one, 28 had a price of, I don't know, 9, and that's going to be type entertainment. Okay, so this is we'll just consider this the database that we're gonna kind of think about as we go forward here. All right, let's see here. So I'll have that in hand. So so we had that. I think I showed you guys before how the classic relational algebra kind of can go into SQL, but now let's look at the actual syntax for doing this kind of gamma operator, the group by syntax, which I think we've already touched on a little bit here, but let's just do it again, and I'll get to that later. So one sec. So now, if we go back to this guy here, so again, that's our signature there. And then what we want to do is we want to have, let's say we want to have the average price at any time. We don't care what time. Average price grouped by the type of stock. Okay, so we might have like retail, entertainment. We might have, let's say, GD, that's General Dynamics. And let me just say that, I don't know what their price was, let's say $11.70. I'm not really sure, but maybe $111.70. And then we'll put them, they're the type, they're type War Pig. So we have the War Pig types, we have the entertainment, and we have the retail. So in other words, we want to say, okay, so the price here is 111. Let's say there's only one War Pig stock, and that is 111 at 70. So then let's just say this holds steady. Let's hope it doesn't go up. Sorry. If it goes up, that's a bad sign. Okay. So we prefer to actually to go down, please. Sorry. But if we want to get the average price grouped by the type, how would we do that? How do we do that in using this aggregation operators in SQL? Okay, so let me see. I'll do that one out. Okay, so so again, we have so basically I'll just do it. Okay, so I'll say here's how we're gonna do it. We're gonna say select basically type, because we want the type, and we want also the average price, and then and then from, and then it's going to be stock. Okay, so there's the signature that we had. So we have the type and we have the price, and then we're getting the average price. Is that going to work? Is that going to work? Is that going to give us? Is this going to give us something like War Pig 111, entertainment? What would it be? 970 or 9 something or other? Maybe. Indeed. Okay, so it was pointed out, that you can't do that. So this, I mean, this is what people will do sometimes, and then they'll say, well, why doesn't it work? And the reason why it doesn't work is because you need to explicitly group by type. Group by type. All right, now that will work. So that will actually do it for us, okay? Now, if you want to say something like, well, we want it so that okay, so notice right here, these are kind of not written so well, but these are timestamps. Normally it would be like 2021, that, and then you do that, and then there's like a colon or something, and then you put in something, and it can go out to like it can go out to many significant digits here. So you can have down to the millisecond or something, even more. If you use extended types, you can do this for kind of physics experiments, and you can take it down to less than a nanosecond, right? I mean, whatever. So, anyways, but there's a certain kind of accuracy on this thing. But let's say that what we want is we want to have them all. We just want the average price in a certain day, right? We want the average price by sector and in a certain day. So, how are we going to do that? Well, it's easy. Well, you want to put it in here, where, and then I was calling it time, is, now strictly speaking, you have to do a greater than less than, or you can use some special functions based on your dialect of SQL that you're using, like if it's PostgreSQL or whatever. But the easy way to basically say this is where, well, I can just say this, where time, here's how you actually do something like this. I can't remember the exact syntax off the top of my head, but something like this. A day. It's not that's not the function, but this is kind of how you would do it. You would say day, and then you're going to apply that function over the time, and you make that equal to some literal, like 2021 0128. Okay, it's not that, this is not the syntax, but you can look up the proper syntax. So what this is doing then is this will apply for all the tuples in the database where this is true, which is the ones that are on that day. Yep. All right. Thank you for people in the chat, by the way, just to kind of tell me that I'm not going to blame it. I'm not going to blame Zoom here, but I should actually look up and kind of see what all right. I wish I could make this big. In fact, maybe I can, but maybe now is not the time to try. Anyways, all right. So, anyways, this is kind of how you would. So you could put the where clause in here. So what that'll do, that's like doing a select in relational algebra. But what this will do is basically it'll go and it'll apply that condition. So it's only going to do this for the tuples that meet this condition in the where clause. Is that clear? Okay. I mean, I'm assuming that's clear. All right. So now, if you want to say something like, okay, well, I want to also have it where I'm particularly interested in the retail and entertainment stocks. Then I would basically say something like this. I'd say where type equals la-di-da, type in, and I can say retail or entertainment. Is this going off then? Okay. Okay. So I can further the conditions here and say and. So all this right here is substituting in there. So it's coming before the group by. So what this does is this further shaves everything down to just tuples that are in those particular types. Is that clear? All right. Now let's say that I want to put a condition on the actual group itself. Right. So I want the average price for stocks where there are at least 200 measures. And remember, they'll probably be for a lot of them, because what we're having here is we're going over these things and we're taking kind of measures at every time interval, every time step. So there's probably going to be a fair number of them. But what'll happen here is that now remember, when we're doing the group by, what we're doing, maybe I'll just do a different piece of paper. Let's just keep it so it's simple here. Oh, here's an easy way to make it simple. Let's forget about all this stuff right here. Okay, let's just look at this right here. So we are getting the types and we're getting the average price. Okay, now if I want to say something like this, if I want to say, give me the types, just give me the types and the average price. We'll start out with a simple one, where the average price is greater than 20. Right, so I don't want to get reports for those that are less than 20. Okay. Let's see here. I don't want the, so does that make clear? So if the average price in that sector for that sector is less than 20, I don't want it to be in there. So what if I just say this? Group by that or that, where, and I'll say this as X. And I say where X is less than 20. Is that going to work? Should probably, uh-oh, did something just happen? You guys can still hear me, right? My Zoom just cut. You can't hear me. Oh, yeah. So the question was something just happened. You said, no, nothing. Well, on my side, something just happened. So anyways, well, hopefully we'll make it through this without any kind of major technical problem. All right, well, group by type, where X equals 20, that's kind of strange because, well, let's see, what does this mean? What does this mean? Yeah, we're clear, I think. Okay. But you guys understand what I want here. I want to get the types where the average price is less than 20. I want the types and the average price when that average price is less than 20. How am I going to do this? Where X is less than 20. Where X is less than 20. So that's kind of weird though, because the where clause goes to stock and there's no X value for stock. So this seems to be a condition that's being applied over the whole group, right? Yeah, so it's not going to work as that. So, but if you do it this way, this will work, right? Having average price less than 20. That will work. Okay, because what the having does, it's saying that apply those conditions to the groups. Okay, to the groups, not to the underlying tuples. So that's what a having does. What about select type average price? No, that won't work. I'm afraid that trying to put the condition up here won't work. SQL will basically barf. Yes, having will always be relative to a grouping. You'll always have grouping and then have having. All right. Now, again, this is a similar thing. That is that this having, strictly speaking, you don't need to have the having. You can do it the following way. All right. Well, let's see here. Leave that open. I don't know why I always start from stock. All right. That's a select star. What kind of star is that? Sorry. All right, what's going on here? What's going on here is I'm using a subquery in a from clause. Okay. And what this is kind of like the way we were doing it in the relational algebra when we had like kind of like we're building up an expression, right? And then this right here, this whole thing right here coughs up a table. Okay, and we're going to call that X. The table is going to be X, and it's going to have an AV for average price, and it's going to have the type of the of the stock, and it's doing the grouping. So it's doing all this stuff internally here, right? And it's going to cough up that X, and then when that whole thing gets coughed up, it's going to then apply the condition over tuples of that thing, and the average less than 20. Okay, so you can always do this, but just like the outer join, it's good to have the halving, because what the halving does then is then it allows the optimizer, the query optimizer, to actually do this kind of evaluation, right? Let's say that there are a gazillion of sectors that have an average price less than 20, right? Then this thing right here is going to be big that's coming back, right? So, but if you were actually able to do it as a halving internally here, as a halving, then the processor, the query processor, could actually do that as it's building the answer, right? So there's, for efficiency reasons, you want to be able to have the halving. Now, this is not the best example here because it probably won't be that big of a deal. But when you get to like megadata, it's good to have a halving, right? It helps the processor do things more efficiently. All right, are we clear? Okay. Yeah, so I think that's all I wanted to. So there's like kind of what they were saying about having clauses, but let's just. I don't think. I mean, you get into some stuff right here where you have some like the conditions in the having. You can have basically arbitrary like condition, subqueries here in havings, but you got to be a little careful about what they reference. Yeah, so that's that. Okay. So going on with SQL now. So that what I think we just covered there over these simple little examples, over this simple little table here. I mean, we can do other ones too. Like okay, yeah. So let's just do this correct here. What about tau? This tau operator. I cannot believe I'm running out of paper here. Okay. So the tau operator was the ordering operator. So how do we order? Let's say we want to order everything by, well, we can say time. That's probably, you might want to do it, order things by time, because right here you have GME. This is ordered by, right now it's ordered by symbol, but we might want to order by time. So how do we do that? We would basically say, so that's basically, we're basically doing our tau operator here now. Select star from stock order by time. Ascending, so from least time, from the earliest to latest, or from the latest to the earliest. Descending. Okay, so you can do it either way. So tau is easy, right? And that's order by. What's nice about order by the way, is that you can have functions in here. So a lot of times you'll have functions over the I mean, you can have arbitrary functions that come into the order by clause, and that can wind up being quite useful and practical. All right. Yeah. So that was the order by. Let's see, what else we got aggregation. I think we've covered aggregation. We have the tau operator. Oh yeah, then there's outer join. And so let's just kind of look at the way outer join works. Basically, you can do outer joins in SQL just pretty much at the in the select. So if for instance I was going to do stock, and then let's say I wanted to do stock, and then I wanted to also have let's say that maybe the customers that own them or something, I could say stock. That wouldn't work. Let's say stock. Well, I'll just give you the syntax. I mean, the example is not going to really work out well. Outer join. Let me see here. Outer join. So let's say that I had that. Yeah, customer. I'll just do it that way. All right. So it's going to basically pair every customer Every stock that doesn't have any owners, it's going to be in there, but it'll get padded by null on this thing in this outer join. It'll get padded by nulls. If there's any customer that doesn't have any stocks, that'll get padded in there. Null. This will be kind of a ridiculous relation, way too large. But then you can also do stuff where you can put in left, or you can put in right. You can put in left here. You can put in right, or you can put in full. Right. So something left outer join, something right outer join, something full outer join. Okay, and then you get the corresponding. I mean, it's kind of like a Cartesian product. It's like you're doing a join here, and then you might want to put conditions inside the where clause to get certain things going. So that's how to use the syntax in terms of getting the outer joins in SQL. Yeah, so we're clear on that. Let's see if we can null values. Okay. I think what I'm going to do here, because we just have a little bit of time left, I'm just going to hop. We'll cover this later. But what we're going to do here also then, and this is the one that's kind of a lot of times will make people kind of squint. It's kind of a little bit painful in its way. But SQL 1999 included recursion. So what you have is this with recursive. So here's the syntax of how we do recursion. So this is exactly that example I was doing before of reachability in a graph. All right, and this is again a directed graph. So that example I had from before, remember when I showed the relational algebra doing the recursive calculation? This is how you do it in SQL. And I'm not sure if all SQLs are going to be giving you recursion at this point. Most will, I think. I need to check on SQLite. I don't recall right off the bat if SQLite gives you recursion yet. I think it does. Anyways, so basically what it says here is it says, here's the base case. So with recursive R, so R is from and to, here's our base case where we're just taking in things from E, and then we're unioning. And then we're basically doing this join between E and R here, right? So you basically have all this right here in the with clause. So this is setting up the recursion. It's setting up the definition of R. And then down here, you can say, okay, well, just give me all the things that are reachable from A, okay? And you're using R here. So it's making a definition of R, and then you're using it in your actual query, right? So that's the syntax on how you get SQL to do that, to do recursion. All right. Okay, so I believe now we have covered the correspondence now between, well, TopCalc and rel-alg and SQL and extended relational algebra. Is there anything I'm missing out in terms of our SQL that I had, that I introduced this stuff in the extended relational algebra? Is there any operations that I have not shown the SQL for? I don't believe so. I think we got them all covered. There was sorting, there was aggregation, there was outer joins. Oh yeah, there is one. That is the delta. And I think maybe I covered this a little bit before, but it's like this delta, the distinct operator, things to turn stuff back from bags to sets. And you just basically do that with a select, say for instance, distinct A from R. And if I said AB, then then it would be all the distinct pairs there. Okay. So now we have the delta operator as well. And I think then now we're clear on that. So what we'll do next time is we're going to go into SQL. We're going to go into kind of SQL as a larger, kind of more practical language, doing the things that we need to do in SQL. And after that, then we're going to look at some design issues, how we actually design the databases. So for instance, and just to kind of get people to kind of warmed up on that, is there anything seriously wrong with this design that I have here? Is there anything seriously disturbingly wrong with this design? I'm telling you there is. I mean, I'm not sure if it's going to mean the end of the world, but me defining the table this way is bad, right? And that is something we're going to be dealing with after that. So this may not seem so bad, but it is. It's bad. Does anybody spontaneously know why it's so bad? I'll give you guys a hint, just something to kind of think about. there's no unique property. Well, first of all, what is the primary key here? The primary key is symbol and time, right? Right? So you can't have GME at, well, maybe you can. You can't have GME at one particular time at one price, and also that same particular time GME being a different price. But maybe later this afternoon it will. Okay, so enough joking. All right. But there's something else seriously wrong with this design. And what if we basically say something like this? I have this one here. I have GME here, and I have GME here, and then I go in here and I just kind of do a little kind of an edit here, and I basically say e-commerce. Okay, that's a problem actually, because now we basically have two records. What type? I ask you now, what type is GME? Is it retail or is it e-commerce? Which is it? Right. You might say, well, because it's later, it's e-commerce, and it seems to me that's where it's headed. And I'm assuming that they'll be selling PlayStation 5s, and I'm thinking I might snap one up from them. But anyways, that's an aside. But what's the problem here is that we've lost some kind of. We'd like to have that certain symbols only have one type, and now it kind of got a little bit munged up here because we have this kind of weird state of the database. So keep that in mind. So the thing is that this might be bad. This might be, and in fact, I think it might be. If we want to have it, so we always have these things classified to one type or another. You might say, oh, well, we would like to have the type evolve through time. Well, if that's the case, then this is fine. But if we don't want it that way, we want to keep these things to discrete types, then we've introduced some kind of anomaly here. All right. And that's something we're going to deal with later about what are those anomalies. We're going to deal with that in very deep terms throughout the rest of the course. But anyway, that's kind of a little bit of a heads up where we're going. Are there any questions before I close the recording and then the meeting? Anything? All right. Okay. I don't see any questions. So therefore, yeah. All right. Well, I'll see you all on Thursday.